Next slide shows the relationship between the speed, radius, and superelevation based on absolute maximum F value. And the sketch on the next slide shows the relationship between the radius, speed, and superelevation based on the desirable maximum F value. Superelevation development is a rotation of pavement from normal crossfall to the superelevated crossfall. Superelevation should be fully developed at either end of circular curves to ensure that a driver does not have to cope with adverse crossfall when entering or exiting the curve. Superelevation should be developed by rotating the road about an axis of rotation. The adopted position of the axis depends on the type of road, the total width of road cross-section, and the terrain. On the single carriageway, major urban road, the cross-section may be rotated about the center line. On divided major urban road, the cross-section may be rotated about one edge of each pavement. In both cases, the presence of public utility services, the necessity to provide access to the abutting properties and intersections, and the necessity to match with levels at the right-of-way boundary may require the use of some other points of rotation. A profile of typical superelevation development is shown on the slide. To improve the appearance, a 20 meters ease rounding is provided that spans the start and end of superelevation development. It is essential that designer consider drainage in the vicinity of points of zero crossfall. Longitudinal grade is required in these areas to ensure that water does not collect on the pavement. Lengths of superelevation development. The lengths required to develop superelevation should be adequate to provide safe and comfortable riding and to ensure a good appearance. The higher the speed or the wider the carriageway, the longer the superelevation development required. Factors that may influence the selection or location of superelevation development lengths include the presence of the structures, the minimum grade required for use of curbs and channels, and a distance between reverse curves and compound curves. The two criteria used to determine the minimum superelevation development lengths are the rate of rotation of road crossfall and a relative change of grade of the carriageway edges with respect to the longitudinal grade of the road. The rate of rotation of pavement desirably should not exceed 2.5% of travel time at the operating speed, but should have an absolute maximum rate of 3.5% per second. These values should be regarded as reasonable values. The minimum superelevation development length to satisfy the rate of rotation criterion can be derived from the expressions. For a rate of rotation of 3.5% per second, which is appropriate for operating speed less than 80 kilometers, the following formula should be used, where E is the superelevation development and V is the speed. For a rate of rotation of 2.5%, which is appropriate for operating speed more than 80 kilometers, okay, the following formula should be used, where L is a superelevation development, where L is a superelevation development length based on the rate of rotation criterion, E1 and E2 crossfall of superelevation at ends of development length, expressed in percentages, And V is an operating speed expressed in kilometers per hour. The relative grade is a percentage difference between the grade of the edge of the carriageway and the grade of the axis of rotation. For a rate of rotation 3.5% per second, which is appropriate for operating speed less than 80 kilometers, the following formula should be used, where WR width from axis of rotation to outside edge of running lane. For the rate of rotation of 2.5% per second, which is appropriate for operating speed more than 80 kilometers, rate of rotation should be determined using the following formula, where WR is a width of axis of rotation to outside edge of running lane. The length of superelevation development to satisfy the relative grade criterion is derived from the following formula. Where L is the length of superelevation development based on the relative grade criterion, E1 and E2 is a crossfall or superelevation at ends of superelevation development length. G is a relative grade expressed in percentages, and WR width for axis of rotation to outside edge of running lane expressed in meters. It is recommended that superelevation development lengths satisfying both criteria, rate of rotation and relative grade, be adopted for design of major urban roads. Adverse crossfall. If normal crossfall on the tangent is maintained around a circular curve, drivers on the outside of the curve will experience constant adverse crossfall. The problem is potentially worse for drivers on the inside of the curve. If they are traveling too quickly, they may cross the center line and experience a change from favorable to adverse crossfall. The effect would be to increase the probability of the drivers losing control. This is not consistent with providing a forgiving roadway. However, curves with adverse crossfall may be required in the following situations: where vertical alignment is controlled by the level of adjacent properties, on a section with a large radius on a very flat grade. In this case, adverse crossfall may be preferable to avoid drainage problems on a large flat areas within a superelevation development and on roundabouts. Minimum radii with adverse crossfall depends on assumed value of the adverse crossfall and the assumed maximum side friction demand with adverse crossfall. The side friction factor demands associated with minimum radii recommended by various guidelines for adverse crossfall generally ranged from 30% to 50% of the normal value. Therefore, it is recommended that 50% of the normal F value be applied in adverse fall conditions. Using the horizontal geometry formula, the resulting minimum radii with adverse crossfall are vary from speeds between 40 to 70 kilometers from 105 to 600 meters. Pavement widening on horizontal curves. Pavements are often widened on curves to permit the same lateral clearance between passing vehicles on a curve as on a straight section of road. The extra tracking width required is a function of a swept pass of the vehicle and allows for such features as the effect of the inside tracking or rear vehicles from overhang and inaccurate steering. The amounts of widening depends on the radius of curve, the type of vehicle operating on the road, and steering allowance. Curve widening is always based on vehicles of the same type meeting or passing each other, even when the incidence of the design vehicle is low. This is primarily in the interest of safety. Lane line marking will therefore accommodate the swept pass of the design vehicle in each lane. Pavement widening on the curves is a difference between the pavement width required on a curve and that used on a mid-block section. The pavement width required on a curve can be calculated using the formula shown on the slide, where N is a number of traffic lanes, U track widths of each design vehicle's meeting or passing, C lateral clearance, F width of front overhang of vehicles, and Z allowance for steering allowance. The curved widening calculation results in a very wide traffic lanes for curves with a radius less than about 100 meters. However, at traffic flows greater than about 1,000 vehicles per day, car tends to form two lanes within traffic lanes greater than about 4.6 meters wide. Therefore, designers should be aware about potential problems that may occur in an urban area with wide traffic lanes due to curve widening. Now we'll talk about the vertical geometry. The level of a road at any point along its route, and therefore its vertical alignment, is usually controlled to a large extent by features that the road passes. The following are the typical controls for vertical geometry: existing topography, geotechnical conditions, existing intersections, property entrances, overpasses and underpasses, pedestrian accesses, service utility assets and their protection requirements, and median openings. The road will have to match within appropriate limits the level that these controls dictate. Vertical clearances both to objects over the road and to provide cover to objects under the road are also vertical control and must be considered for the whole road cross-section. Changes in a crossfall or superelevation, position of a road crown, addition or removal of traffic lanes, and the angle between the road and the object can have all a bearing on a vertical clearance and must be checked for compliance with the clearance standards. The impact of future surfacing requirements on vertical clearances should also be considered. Great.